This video is a follow-up to the previous video that you just watched on states of matter. So this is going to have us look a little bit more in detail at sort of a molecular, atomic molecular level picture of what we mean by states of matter. So from the molecular viewpoint then, let's think about the difference between solids, liquids, and gases. Shown here is this setting, different seasons of the year. So here we've got solid water, ice and snow. So what's different at the molecular level between solids, liquids, and gases? Well, first off, we know that solids have a definite shape, right? Well, why do they have that? Well, that's because the molecules are locked into position. So in this case, we've got water molecules here. Each water molecule will interact with other water molecules through these intermolecular forces that we'll talk about next semester, actually. And these forces help hold the water molecules rigidly together in this structure. So they kind of can move around just a little bit, so they sort of vibrate in place, sort of shake around, jostle about, but they don't really move, so they're not free to move. That's why the water can't spread out like liquid water can. So there are all these interactions. That's what holds the water molecules together. And so in this case, these water molecules are moving a little bit, but they don't have a lot of energy of motion. So there's not a lot of energy of motion in this case. An analogy that I often use in thinking about how solids, liquids, and gases differ at the molecular level is to think about people that are packed, that are interacting in different situations. So in this case, we're going to think about the subway system in Tokyo, Japan at rush hour. So you may not have been there, but at rush hour they actually have officials whose job it is to take people and push them into the subway cars enough so that the doors can close. So when you're in the subway in Tokyo in rush hour, you are packed together. So as the train moves along, you can't move, but you do get jostled about, bumping into your neighbors. So you're lots of strong interactions. That's what's going on here in solids. So in contrast with liquid water, you still see that there are these attractions between these molecules. Well, that's what keeps all the molecules together in the liquid. But these attractions are constantly breaking and reforming. So there's a lot more energy of motion here. So these molecules are free to move around. They can tumble about each other, constantly bumping into each other, making little interactions and then breaking those. And that's why water is allowed to spread out, but the molecules can't altogether leave because they're held by these attractions. The analogy here might be the sidewalks of New York City during rush hour. So, packed with people, but there's flow. You're interacting, bumping into people often, but it's hard to get around because it's so crowded, but there's movement. And then finally, the highest energy state is the gas. So in this case, the molecules are far apart from each other, far enough apart that they don't interact. And it's kind of rare that you bump into another molecule to have an interaction. This would be a high energy state. These molecules are moving fast and moving around, not bumping into each other very much. And when they do, the interactions are kind of fleeting. The analogy here might be folks wandering around in the country out here in rural Illinois, right? It's rare that you're going to bump into anybody else, maybe a cow or a pig or something, but it's rare that you'll bump into anything else, certainly corn and soybeans. But anyway, so that's the difference between the molecular level pictures, the solid, liquid, and the gas. The last video talked a little bit about these terms, and we just looked at the molecular level viewpoint and talked something about energies. So this is a diagram from your textbook that shows the different states of matter and how you can convert from one to another through different processes. And these are the names of the processes, like sublimation, vaporization, condensation, deposition, melting, and freezing. Now sometimes for melting and freezing there are a couple of other terms you might hear. A slightly fancier term for melting is called fusion, and a slightly fancier term for freezing is called solidification. So you might hear those terms as well. So we have these different processes where we can convert from one type into another type and back and forth. This diagram also shows you roughly the relative energies of these substances. So solids have the lowest energies of motion, so they're down here. You have to add energy, you convert them to a liquid. More energy still converts them into a gas. So this ranks the different substances, different phases, not substances, phases, based on their relative energies. And finally, let's see if we can answer these questions. So, question A, shown here molecular level pictures, what kind of phase change is depicted by this process, starting in this box and going to this box. Well, if you said freezing or solidification, you would be correct. Very good. So here we see molecules. They're obviously attracted to each other. Can't really see motion here, but it's not an ordered array, and we see that they fill up the entire container. So probably this is a liquid, right? Then when we go to this situation, all these molecules are packed together in a nice orderly arrangement. They do not expand to flow out and fill their container, so there's no flow. They have definite size, so that is probably a solid. So going from liquid to solid, we call that process freezing or solidification. So what process do you think is going on in B here? Okay, if you said sublimation, you would be correct, right? So we've got a solid here, orderly grouping of these molecules, not expanding to fill the whole space, rigidly locked in place, and then they're going to this situation where they expand to fill the whole container. They're separated, well separated from each other and moving about. So that's a gas. So solid to gas, that process is called sublimation.